Hello, I'm here to help you today a little with piecewise functions. We have two lessons that lead into the graphing of piecewise function. In worksheet 1.5, we'll be focusing on just students learning to restrict the domain and graph only part of a function. So this is the worksheet 1.5 and what this looks like. And the first thing we have them do is just plug a number in to the function. So if I was going to plug -2 in and square it, I would get 4. And that is actually practicing this notation and giving them a value that they're actually going to start their graph at. Then the second thing they need to notice is we're going to graph this equation, but we're only going to graph it where x is greater than -2. So there's a lot of ways that you might show this. I usually begin by showing my students a very light dotted line at x equals -2. And this is sort of the dividing line. We want to graph where x is greater than -2, so we're going to graph on this side. This side is no man's land. We are not allowed to go over on that side. And we know that when we're at -2, at this line, this function would be at the point -2, 4. Now, so basically what just happened here is we plugged in -2, we got out 4. That's a point. The problem is we aren't really supposed to graph that point. We're only supposed to graph where x is greater than -2. So what I would do is at the point -2, 4, I'd put an open circle. So we're not going to include that point, but we do want to include -1.99, -1.999, everything just barely before -2. And then this is going to be a parabola with a vertex at 0, 0. We'll go up 1 over 1, up 1 over 1. And then this is up 3 over 1, up 3 over 1. The next one would be up 5 over 1. And so this would be our graph only on this side where we are supposed to be graphing where x really is greater than -2. So we have a piece of a parabola there. Then they're going to ask for the student to state the domain and range in interval notation. In this case, the domain would be from -2 but not including -2. And the x's continue to go on and on all the way to infinity. And the range, a lot of students, one thing you'll see is they'll automatically pick this number 4 like they're supposed to use that in an answer because we use the -2. But in this case, the lowest y you can see is 0. We did actually get to 0. And the highest y going up forever is infinity. So that would be the domain and range. And throughout the whole worksheet, that's pretty much how it works. You'll see here you have a piece of a line. We didn't include -1, so there's an open circle there. You have a piece of a parabola. We did include this point because there was an equals to right there, so that point was included. You have a piece of a line. This one, number 5, is a case where you're between two numbers. You're between 0 and 6. That's my domain. Notice it is not including 0, and it is including 6. And then this f of x equals -3. Sometimes students have trouble plugging into a function like this, and so I just tell them when I plug in 0, f of x does not care, it gives -3. When I plug in 6, f of x does not care, it gives -3. And all the way in between, it's going to be -3, a constant function with an open and a closed. And so then there's a lot of different ways you can write the range when it's only one number, or the domain when it's only one number. A really common way you'll see in interval notation in college textbooks or higher textbooks is to go into set notation, because the truth is we don't have an interval for this range. We only have a single value. And so interval notation doesn't really work if your answer is not an interval. So this is set notation, and some of you might be used to that from the higher courses that you teach, and that's fine. Some of you might like y equals -3. Some of you might not like the y equals because that makes it seem like the whole line of that. And some of you might just take -3 for the range, assuming that it's y value because it's the range. So a little bit of flexibility on that. You're not going to see that as a test question. You won't see things expressed this way on a test, so it's your choice. Okay. This one's a little odd because only the value of -1 is excluded. So we have the entire absolute value function. Before -1 was happy, after -1 was happy, only at -1 did we have a problem, and so we graphed that whole function, and to show that I'm leaving out the value at -1, I put an open circle. And the worksheet just continues like that all the way through. We have a piece of an exponential, a piece of a parabola, a piece of an exponential between two numbers, etc. Okay. And then we go on to worksheet 6, and worksheet 6 is going to show you piecewise-defined functions. This is called piecewise because the function has two pieces. One piece that's going to be like y equals 4, one piece that's going to be like y equals 2x plus 3, and they're defined over different intervals. And so I'm going to show you a few examples. Some of them I'm not going to work all the way through, but they are examples you could use for your notes if you were wanting to do traditional notes. Here is a first example for worksheet 1.6. So when I teach this, I personally call this the dividing point, the place where we change from one function to another function. I don't know if that's an official name that works for me. And so at this place, the rule is going to change when x equals 1. So for my own ease, I put a little dotted line there. This is not an asymptote. This is not anything like that. It's just helping me to remember where the rule changes. And when x is less than 1, I'm going to use this top rule. So that's going to be like y equals 2. And when x is greater than or equal to 1, I'm going to use this bottom rule. So that's going to be like y equals x minus 3. So I have two separate graphs that are going on. I've always had students struggle with graphing piecewise functions, but this was the first year that I did worksheet 5 ahead, or anything like worksheet 5 ahead of piecewise functions, and my students seemed to just take it all in stride. I was ready for it to be a really hard lesson, and after worksheet 5 they didn't seem to have anywhere near as much trouble. I hope you have that experience as well. So what I tend to do is just think about what point I'm going to get. I prefer to write an XY table, but it would be great if you wrote f of and got used to function notation also. So I'm wondering what happens at this dividing line when x equals 1. And this function is y equals 2. It equals 2 always. And I'm wondering here what happens also in that case. Let me do a different color so we have two different colors going. Well, I don't think it matters. So I'm going to plug in 1 right there, and when I go 1 minus 3, I'm getting negative 2. So when I plugged in 1, I got negative 2. So I have two different points. Now you might have thought I shouldn't really be using 1 because x has to be less than 1. So I'm going to put little parentheses around there to remind myself of that. But I am going to use everything up to 1. So I want to use 0.9, 0.99, all those things up to 1. So on this side, I'm graphing the line y equals 2. That'll be a horizontal line, and it'll just be going nicely along here all the way until I get to the point 1, 2, when I need to make an open circle, because that is not included. It's going to go forever in that direction. And then I'm going to jump to this line. This line is a line with a slope of 1 and a y-intercept of negative 3. Now notice that's not the most convenient way to graph this, because if I put the y-intercept of negative 3, I'm in the area that is not allowed for this function. So negative 3, that y-intercept isn't really a useful point for me, and it's going to be a little bit easier to start from this point that actually is included in this graph. So 1, negative 2, I'll make a solid dot right there, and then I'm going to count my slope from that spot, which is going to be up 1 over 1, up 1 over 1. And I'll just go ahead and do that line. And this is a piecewise function. This piecewise function is called discontinuous because it is broken in two separate pieces. That's going to be a word we're going to be using. Actually, continuous is a word we're going to use in the second chapter. It's good to introduce it now. A function's continuous if the two pieces connect with each other. This one's discontinuous because the two pieces didn't connect, or you can just say not continuous. The two pieces didn't connect. The kids have heard that word before. They learned that in Math 1 in Unit 0, but they probably haven't used it much since then. This is really one of the first good examples of continuous and discontinuous functions that they've run into since that time, and so it's a good vocabulary piece. They will be tested on that in Unit 2. Okay. And if we're going to do domain and range on this, notice that my domain, even though 1 isn't included here, it is included here. If I come along with a 1 and I want to plug in f of 1, I do have a place that I'm allowed to plug that into. And so my domain is going to be from negative infinity, and 1 will work, all the way to infinity. And my range, the lowest y that I have, is negative 2, and I do actually hit that. And some people are worried about this open circle. Yeah, there's one spot where y does not equal 2, but there's a lot of spots where y does equal 2. And so it's okay, y can be 2, and it's going to keep going up for forever on this side, and so we'll be able to get really high y values. So that is the range. One thing you should notice is that this function does pass the vertical line test. There's this spot here, but it only hits one of these 2 points. If this was filled in, then it wouldn't be a function, and in fact you will always have equations that are functions on this worksheet, so that's a good test for the kids. If they accidentally fill things in, then they might have 2 points over each other. And so sometimes kids wonder, why did this one get the equals and this one not? And it's just very important that they don't both have an equals, because only one of those can have a y output for x equals 1. All right, here's another example. I'm not going to work through this one all the way, but here we go. But if you want to copy that down quickly for your notes, I have a function. The things that I did tricky right here were I changed the order of this, so the kids had to notice that x was greater than 1. Greater than or equal to 1 was over here, this parabola piece was over here, and the absolute value piece was over there. Notice that I had to white it out because I fooled my own self, accidentally wrote it down the wrong way. And then another interesting piece happens because the dividing point is the same for both of these functions. And so when I graphed this absolute value piece, I had an open circle at 1, 1 because there was no equals there. But when I went to graph the parabola, that open circle got filled in by his point 1, 1. And so this did end up being a continuous function because the 2 pieces connected, and my domain was from negative infinity to infinity, and my range was from 0 to infinity. Again, students will want to use 1 because when they plugged in they got 1, they think maybe 1 should be a number in the range, but they need to look visually and see that the lowest spot that this graph gets to is actually 0, and it does get there, so it's included. And the last thing you need to worry about is sometimes there's 3-piece functions, and so I get an example of a 3-piece function here for you. And that means there's 2 different places where the rules change. So one happens when x is 0, so again I'm going to just make myself a tiny dotted line there. And when x is less than 0, I'm using this parabola, this quadratic function. And then from 0 to 3, the next place where the rule changes is at 3. 1, 2, 3. And between 0 and 3, it looks like I'm using this rule, y equals negative x minus 3. And then after 3, I'm using this 2. So this is y equals 2. Not forever, though, only until 6. So you might want to have the dotted line at 6. Let's see, is that right? 1, 2, 3, 4, 5, 6. Yes, it is. Just to remind yourself to not go on forever after that. There's nothing going to happen over here past 6 because this function is only defined up to 6. Its domain is not going to go past that. But it might just help you to have that line there to remind yourself to stop. Okay, so we're going to do each one of these graphs and then we'll be done. So here I know that I have a parabola. It looks like it has a shift back 2 and up 1 for the vertex. So there would be my vertex. It'll be facing up because this is positive. And so I would go up 1, over 1, and up 1, back 1. From there up 3, 1, 2, 3, over 1. Let's see, wait, I didn't quite make it over 1 the last time. There we go, and back 1. And so this will be my parabola. I do need to get this dividing point so I can know exactly where I'm hitting. When I plug in 0 here, I'm going to get 2 squared plus 1, so 5. 1, 2, 3, 4, 5. I should be hitting right there with an open circle. I almost forgot that. Let me make that a bit more clear. This is going to be an open circle right there. And so this parabola then will come along like this. That spot. After that, we'll go to this next line right here. In this particular case, the y-axis is right on the edge of this domain for this function, and so I can use slope-intercept to graph. My y-intercept is -3, and I'm going to include that. If you like to write it like this, just to have it be consistent in how you do that, when I plug in 0 here, I'm going to get -3. When I plug in 3 here, I'm going to get -6. So I will have 0, -3. This one will be solid. This one will be open. So 0, -3 will be solid. And it looks like I need to make my graph a little bit longer. I undershot. 1, 2, 3, 4, 5, 6. And so then when I get to this line, this one would be open at 3, 6. And this is a straight line, so that would be my second piece, solid, open. And then for my third piece, I have y equals 2, and y equals 2 is a horizontal line at 2. Notice that both of these are filled in, so if you are wanting to continue this for consistency's sake, when I plug in 3, I get 2. When I plug in 6, I get 2. This function doesn't care. It is always 2. So I will have a solid dot at 3, 2, a solid dot at 6, 2, and I'll connect those. And here we have a piecewise function. This is definitely a discontinuous function, not connected, the 3 pieces. Even if 2 of them were connected and 1 was not, that still would be discontinuous as a function. And just to clear up, that was open, this was solid, this was open, and this was solid. And so you can see at each vertical line I'm only hitting 1 point. I'm only hitting 1 point. My domain would be from negative infinity, because this one's going on forever. Yes, I do have a value at 0. Yes, I do have a value at 3, all the way to 6, and it includes 6. And my range would be, the lowest value is here at negative 6, and so I would not include it, so I'd have negative 6. And the highest value, let's see, is there, there's a little gap where there's no y value. So it's going to go negative 6 to negative 3. Negative 3 was included. And then it's going to have a second piece. It's commonly written with a little union sign. I don't think that's the end of the world there, but that's the common notation for that. And the next lowest y value, as we look, is this one right here at 1. We do hit that. So then we would have from 1, and we have a lot of points where y equals 2, all of these plus 2 over here, but that's still just one value that y is allowed to be. Y is not allowed to be 5 right here, but it is over here, so you are definitely allowed, and this is going to go up forever, so all the way to infinity. And so this would be the range, and that's pretty tricky. That's probably the hardest one that you will see. I don't even know if you see one that difficult. As you keep looking at Unit 6, you get a lot of practice graphing piecewise, a lot of practice graphing piecewise. And then on an earlier video we talked about practicing writing piecewise functions. That happens on 14 and 15. Students often will write this as 2 separate, f of x equals, f of x equals. They need to know that that is all one piece. Okay. And practicing the types of functions here. This one is called a step function. It's really not any different than everything we just did, except for that all the pieces are flat. So I have from 1 to 3, which would be somewhere in here. Okay, this pen doesn't want to write. There we go. From 1 to 3, I would have y equals 2. From 3 to 5, I would have y equals 4. And from 5 to 7, I would have y equals 6. And so y equals 2 is a nice flat horizontal line. I'm going to have an open at 1 and a closed at 3. Y equals 4 is another horizontal line, just 2 up. I'm going to have an open at 3, still passing the vertical line test, and I'm going to have an open at 5. That would be my y equals 4 piece. And then y equals 6, I'm going to have a closed at 5 and an open at 7. Okay. And this is called a step function because it looks like steps. That's really a common type of function. In real life problems, you can see things where your rate plan jumps up. For this many kilowatts you use, you're under this rate, and then when you use the next amount, you're under this rate, and like that. Sometimes it seems like quite a big jump. And you do actually have a word problem where the students will write a piecewise function that is a step function like that, and then go on. All right, so I wish you good luck with those, with the worksheets 5 and worksheet 6, and that'll be the end of this unit.